Okay, good morning, everybody. Today we are going to discuss dynamic programming. Dynamic programming is a very powerful design strategy, and it's used to take problems that seem on the surface to be exponential time, using a sort of a natural implementation of them and reducing them to polynomial time. Often, instead of it being, let's say 2 to the n, you can get it down to n squared. Instead of it being 3 to the n, you can get it down to n cubed. All right. Okay, let's just do this here. So this is from the winter course. We looked at these together. Okay, so these are some of the strategies we've seen in this course so far. One of them that I may not have mentioned before is a transform and conquer. So anyone know what transform and conquer means? It means you change the format of the problem and then you do it. So an example of that would be, let's say, pre-sorting, where you take the data and you sort it. And then once it's sorted, you're able to do that. So we saw that, let's say, with the closest point problem, right? Once you sort it, it's very easy to figure out where the closest pair is or where the furthest pair is, right? So that's an example of transform and conquer, where you either change the input or you change the output or something and make it different. Okay, so here is a quote. It's a famous quote, and it's also famously applied to dynamic programming, right? So it's attributed to Georgia Santayana, and it says, "Those who do not learn history," or sometimes they say do not learn from history, "are doomed to repeat it." The idea is, and applied to computer science, that if your algorithm is doing the same thing multiple times and you don't realize that it's doing it multiple times, so now you're going to do it multiple times and it's going to take too long. So if there's some way to remember what it is that we're doing, or better yet, to organize our code in such a way that you never have to repeat something to begin with, so then your program will run more efficiently. So that's really what this is about. All right, so here we have a quote about the quote. I'll let you look at that on your own. Right, so what is dynamic programming? All right. Dynamic programming is a response to generally what we call top-down program, which includes recursive code. So recursive code is often top-down, right? You start with the n case and you do the n over 2 case or the n-1 case, and you work your way down, right? So in dynamic programming, we start with the smaller cases and we work our way up, all right? Already yesterday, we saw an example of that with the 0-1 knapsack problem with integer weight capacity. And we said that we gradually increase the capacity, right? So we go upward instead of downward, all right? Now, this assumes that the structure of the problem is so that it has what's called the optimal substructure, right? Where the bigger problem does depend on the solutions to the smaller problem. Sometimes the bigger problem becomes a different problem, and then dynamic programming is not going to work. All right, so an example of this optimal substructure is the all pairs shortest path problem. That means I want to know, I have a bunch of vertices or points or cities, and I want to know how to get from each city to every other city the fastest way. So it turns out that the fastest way of getting to every city depends on how to get to cities that are closer. So that's what we call optimal substructure. For other problems, such as what's called the traveling salesman problem, where I need to go from one city to every other city in one cycle, right? That does not have optimal substructure. So dynamic programming is not going to work, at least not for the optimal solution. Okay, so let's take some examples, right? And let's say I wanted to compute the closest triple. Okay, and let's say we define distance by looking at the difference between the x's of 2 points, the x's of 2 other points, and the x's of the third point. Sort of like the size of a triangle, right? You look at the size of 1, 2, and 3. Okay, can someone tell me how long it would take to do this? In other words, if I gave this to you on a quiz right now, I'm not doing it. Let's say I gave you this question on a quiz. You should be able to solve this, but your solution may not be so fast. You should be able to solve this. What would you do? So you might have a triple nested loop, right? You might say something like for I equals 1 to 10, for j equals 1 to 10, for k equals 1 to 10. And then you compute this formula and you check if it's less than the previous min, then that becomes the min, and you keep on going. So what's the time complexity of that?
O cubed.
O of n cubed. Good. All right. Does anyone see some sort of a wasted, I'm not saying it's going to be necessarily less than the n cube, but there's still some waste that's going on there. So here's the waste. The waste is that I end up computing the difference between xi and xj multiple times, right? For every value of k, I need to recompute this. So a better approach would be to compute all the pairs, right? And how long will it take to get all the pairs? All right, we did. Go ahead.
O of n squared.
O of n squared. Good. Now, once I have all the pairs, when I do my nested loop, and it's still going to be a nested loop, I can just refer to those differences I already calculated. So it's still going to be O of n cubed using this approach, but I am not redoing the same work. All right, so that's an example. Right, so here is my option 1, do 3 levels of nested loops. I compute all the distances between the pairs, right? And then I use it for the triples, okay? And fine, okay. So now we're going to get to one where you can really see the improvement of dynamic programming, all right? So we have one of the most famous series in mathematics called the Fibonacci sequence, right? The first value in the sequence is 0, the second one is 1, and each subsequent one is defined as the sum of the previous 2. And this is a famous series. It shows up in all kinds of things, math, biology, art. It also shows up strangely or unexpectedly in the analysis of things in computer science. So not just when you're looking at Fibonacci numbers, but other things. So we saw the other day, we saw something called a Fibonacci heap. The Fibonacci heap is based on the fact that the analysis of the heap, relates to Fibonacci numbers. There's something called a Fibonacci search, right? So we did search algorithms at the beginning of the semester. There's a Fibonacci search, right? So they show up unexpectedly in different cases. Okay, so here we see some nice illustrations of Fibonacci patterns. All right, and you could write this code very easily, right? So intro student should be able to implement this, right? You have your 2 base cases, and then you have your recursive case. Okay, what is wrong with this? On the surface, it looks very right. So let me show you what's wrong. Take a look at this picture here. Okay, this is an example of the recursion, the stack, right? The function calls. And you'll see that to compute f of 5, I need to get f of 3 and f of 4. But to get f of 4, I'm going to need to get f of 3 and f of 2. But I'm also computing f of 2 over here, and I'm also computing f of 3 over here, right? F of 3, I need to get f2 of f and f1, but I'm computing f of 2 over here. I'm computing it over here. I'm computing over here. So I'm computing a lot of things multiple times, and that's a bad sign. So what we're going to do is we're going to do some analysis here. and I say, okay, what is the cost? How many additions do I need to do this Fibonacci approach? So I say, okay, well, to compute f of n minus 1, if t is the time to compute f of n, then t of n minus 1 is the time to compute f of n minus 1. And if I need to compute f of Fibonacci of n minus 2, that's going to take n minus 2, and then one more. Why one more? Because I need to add them together. So it's the time to do this, the time to do that, and one more to add them together. Okay, so we have a recurrence equation. Anyone know how to solve that? Probably not. Okay, that's not so easy to solve. But what we can do is we can bound it. So we can say as follows: t of n minus 1 and t of n minus 2 is less than t of n minus 1 and t of n minus 1. Why is that true? Because t of n minus 2 is obviously going to be a smaller number than t of n minus 1. Similarly, t of n minus 1 and t of n minus 2 is going to be bigger than t of n minus 2 and t of n minus 2, because t of n minus 2 is the same as t of n minus 2, but t of n minus 1 is bigger than t of n minus 2. So we have 2tn minus 2 over here, plus the 1, and we have 2tn minus 1 over here. And if you do the math here, you can understand why this is going to be. I'm sorry, let's start with this side first. That's the easier side, is t to the n, 2 to the n. Why 2 to the n? Because each time it's 2 times the previous one. So if I keep subtracting 1 and multiplying by 2 at the same time, I'll end up with 2 to the n. So this side here is going to be 2 to the n. This side here is 2 to the n over 2. Why 2 to the n over 2? Because we keep multiplying by 2, but how many times do we decrement it? Each time we do 2 times, right? So it's going to be, we're only going to subtract off 2 and over 2 times. So the left-hand side is 2 to the n. The right-hand side is 1 to the square root of n. Sorry, it's a square root of n, square root of 2 to the n. So we're somewhere between 1.4 to the n and 2 to the n. And the answer is we're actually, comes out to be around 1.6 to the n. Okay, so again, we're able to, in our head, without doing, without a calculator, we can figure out that the left-hand side is around 1.4 to the n, right-hand side is around 2 to the n. So we're somewhere in between. It comes out to be about 1.6 to the n. So does anyone have another suggestion? How we can code Fibonacci so that it's not exponential time?
Hey, you can keep a hash map or array of like the answers every time you compute it, and you can just consult.
Okay, so a hash map is probably overkill, but yeah, if we keep an array of whatever we computed so far, right? So that's what we do here. Okay, so we initiate a array of size n plus 1. We set the first one's already going to be 0 from this initialization. Second one will be 1, and then we iterate over the remaining ones, and we always store each result, which is the sum of the previous 2, and now we have it. So when we get to the next step in the loop, right, we have the previous 2 and we just use them. We don't need to recursively compute them. So what's our time complexity now?
O of n?
O of n, right? So that's an amazing improvement, right? We went from 1.6 to the n exponential time to order of n linear time. Now that's sort of obvious. In other words, if I gave you the Fibonacci program and I said do it recursively, you could probably do the recursive algorithm without our lecture today. If I said, you know what, recursion isn't so good, come up with an iterative approach, you probably could come up with an iterative approach even if I didn't have a slide. But some of the other problems that we talk about today are not so obvious. So that's why we need this lecture. Right, the next one is something called the maximum sum subarray. And it says, let's assume we have an array of positive, negative, and 0 numbers. All right. And a subarray means not the whole thing, right? I mean, it can include the whole thing, but it doesn't have to be the whole thing. It's a subarray. Okay, notice it has to be contiguous, which means I can't skip around, right? So I want to know what subarray will give me the largest possible sum. So let's just take a scenario. Let's say all the numbers were positive. What would be the maximum sum subarray if they were all positive numbers?
The entire list.
Just take the whole array, the whole list. Good. What would happen if it could be positive or 0?
Still the entire list.
Still the entire list. Good.
0.
Now, why does negative throw things off?
Since potentially if you add a negative in the middle, you could be adding bigger positives together.
Okay, right. So let's take this sub list here. If I go from 8 to 2, I get something. I don't know what that adds up to. I guess it says down here 16. If I add -5, I get -11. Okay. So sometimes it's worthwhile and sometimes it's not. So for example, this -3 is worthwhile to include. Why? Because if I include the -3, then I can also include the 8 to the left. Okay, so we call this the maximum subarray. So how do we find that? How do we find, where to begin and where to end so that we maximize that sum? So if you didn't know dynamic programming and you've never seen this before, by the way, there's a name for this. It's called Kadane's algorithm, and it's been around for a while, several decades. What could you do? Again, I'm not looking for the best possible answer, but an answer. So by the way, some of you have already interviewed, some of you will be going on interviews. So the worst thing you can do is not have anything to say, right? Because then it looks like you don't care, you're not trying. What you can do is you start with, an obvious solution, and then you talk about how there might be better solutions, and you try to, think about that. But you should always have some kind of answer. So what is a not necessarily optimal answer, but something that would solve the problem?
Starting with the first element, you can generate every subarray until the last element.
Okay, so and how many subarrays are there? So basically think of a subarray as you specify the beginning position and the ending position. So there are going to be n choose 2 or n times n minus 1 divided by 2 possible subarrays. Sorry, my previous class's recording just completed. I need to respond to that, and then I will be back with you. I just say okay, okay, okay. Good. All right, so I could do that, and then for each subarray, I need to add up the sum, and I look at the one that is the largest, and I have my answer. Right. The problem is there's a lot of overlapping subarrays there, so I don't necessarily. I realize, maybe that's not the most efficient, but it will give you an answer. Okay, so that's what this is saying. It's brute force. You look at all n squared possible, or n choose 2 possible subarrays. For each one, you need to add them up, so you get O of n cubed. Okay, so you suspect that that's too much, but it is an answer. Here's dynamic programming. Okay, what dynamic programming says is we're going to go one pass through the array, right? There's one loop, and that's it. And we ask ourselves the following question, 2 questions actually. Okay, one question is reflected in this line of code. Second one is reflected in this line of code. It says, does taking the next number make it bigger or not? Okay, if it makes it bigger, then great. If it doesn't, don't use it. Okay, then we say, take our best sum up until this point and see if it's better. I'm saying take the sum up until this point, and is it better than whatever best sum I had overall? So those are the 2 things that are happening here, right? Look at the code. It says, if I take my current sum and I add X, if it's more than 0, then we're happy. Okay, so that would be our current sum. Because 0 is always better than anything, is better than any negative. So if I get something positive, I say that's my current sum for this position, including this position. And I say, is it better or worse than whatever best I had so far? All right. So now we're doing it in one pass, right? This is obviously an O of n algorithm, right? 2 operations, because I got a max here, a max there, if you want to count the loop. So that's a 3rd operation, some kind of check to see if we're done, right? So it's order of n time. Okay, so that's improvement. I wouldn't say it's obvious. It's not the most difficult problem, but it's also not obvious. So we have that Kadane. By the way, In the past, I'm not telling you it's going to be on your final exam, but a question that I've asked on past finals is, what algorithms have we learned in this course that begin with a K? So either by the name of the person or by the name of the algorithm, right? So we had a Kidane, we're going to have a CARP, Karatsuba, right? We have the knapsack problem. So just to sort of see, if you remember stuff. Okay, so now we're going to move on to a very interesting problem. One that if you could solve it at all, you would probably use recursion, and recursion is going to be way too expensive. So this thing is called the longest palindromic subsequence, okay? And they're calling it LPS, or I'm calling it LPS here. In an assignment, I'm actually changing it to LPSSQ because there's going to be sort of another problem we're solving simultaneously called the longest palindromic substring, and that also begins with an S. So that one we're calling LPSST. All right, but for now, it's in these slides, it's just LPS. Okay, so first of all, you have to, if you want to talk about a longest palindromic subsequence, you have to understand what a palindrome is. What is a palindrome?
Same forwards and backwards.
So it's a string that's the same forwards and backwards. Usually comes up a little bit in some of your courses. If you've taken CS 320, it's a very important problem there, right? Because you talk about regular languages, you can't detect palindromes. In context-free languages, you can detect palindromes, you can generate palindromes, right? So it's an important topic in the theory as well. Right, so that's a classic example that is race car, okay? But here's the thing. In a palindromic subsequence, the letters do not have to be contiguous. You can't change the order, but you can skip. You can skip around, right? So take a look on the bottom here. We have, let's say you take the word Queens College of CUNY. So I didn't run this through a program, but can anyone tell me the longest palindromic substring? Substring means contiguous, without skipping any letters. So I think it's 3, but I have been wrong on these things before, where students, visually found ones that bigger than my vision. So the longest substring that is, a palindrome. So I think it's 3. I think it's an EGE. Anyone see anything bigger than that? Okay, I'll take that as a no. All right, what is the longest palindromic subsequence? So this is harder, right? Here's one with 8 letters. Okay, so you got U, E, E, L, L, and then E, E, U. Notice that we don't have to, we're allowed to skip. Okay, then we have this one here. This one is N, C, O, E, G, E, and then the other side of it, O, C, N. All right, so that's a palindromic subsequence with 9 letters. So, but this is an algorithms course. It's not a, how smart you are, visually course. So we want to write an algorithm for it. So here's what we're going to do. And the way many, okay, so first of all, you could do exhaustive search. Exhaustive search means you check every possible subsequence, and they're going to be 2 to the n subsequences. Why are there 2 to the n subsequences? I'll give you an, it's sort of like subsets when you deal with, right, for each letter, I can either include it or exclude it, include, exclude, right? So that's the 2 to the n. So I could take my 2 to the n subsequence, look at it, see if it's a palindrome. That takes O of n time to determine if a string is a palindrome. So I get n times O to the 2 to the n, or n times 2 to the n. And that is really bad, okay? That's worse than exponential. Okay, so here's what we do, okay? We're going to define it recursively, and we say as follows. If I have one character, okay, so meaning position I to position I, one character, what is the longest palindromic subsequence of that? How many characters? So it says in the slide 1. Can someone tell me why? So Young Ying, why is that 1? Or anyone else? Why is the longest palindromic subsequence? It's only one character, and one character is always a palindrome, right? One character is always a palindrome. Okay, what about going from I to I plus 1, meaning 2 characters? So there are 2 possibilities, right? One possibility is the 2 characters are the same, AA, BB, CC, and so on. So if they're both the same, then it's 2. What happens if they're different? So what is the longest palindromic subsequence of, let's say, AB? Right, so for AB, what is the LPS of that? 1. Why, Ming? Why is it 1? Why isn't it 0?
Because the subsequence can be A or B.
Correct. Okay, A is valid and B is valid. Okay, so you can't use both, but you could use either one. All right, now we get to the more general case. In the more general case, we're going from I to J. So watch this. We say, well, if the 2 endpoints are the same, then I get those 2 characters and the 2 endpoints and whatever I could do in between them. So it's the LPS of I plus 1 to J minus 1 plus 2 for the endpoints. And the LPS of IJ is going to be the left or the right if they're not the same. In other words, if the 2 endpoints are not the same, either I omit the right end or I omit the left end and see how well I can do with those. All right, so that's the formula. Okay, so if I convert that formula into a program, I call it LPS. Okay, so if the 2 positions are the same position, right? I and J are the same, not in the same letter, the same position, I return 1. If they are 1 apart, right? So I plus 1 equals J, then I return 2. Okay, fine. If the generic case, right? If the 2 endpoints are the same, by the way, should I get rid of my parentheses here? Right, so if the 2 endpoints are the same, then I get 2 plus whatever I had before. And if the 2 endpoints are not, then I have to take the max of those 2 cases. All right, so what I'm doing in this slide is I am taking the recursive definition. Right, so that's one of the things you do in 220 and 320. You talk about recursive definition. So we're taking the recursive definition and converting it into a recursive program. Okay, can anyone tell me what the time complexity of this is going to be?
O(n) squared?
Well, that would be nice. Okay, so I don't have a complexity analysis here. So it's going to be exponential time. Okay, it's going to be exponential time because what you're doing here in the generic case, it's going to look something like this. If n is the number of characters in the subsequence, basically, so let's say this, right? It's T of I comma J, right, is equal to, we'll call it S of n, okay, where, and there's like a domain transformation is equal to the number of characters. So it's going to be I minus, you know what, instead of just writing it in the chat, let's write it in the slide itself. So I don't think I have it. Do I have an analysis here? No. Okay, so let's do an analysis here. Okay. I duplicate the slide. Come on. Okay, so let's say, I'm going to write it the other way here. Okay. let's make this a little bigger. Okay, so let's say S of I comma j is the time to solve, let's say, to compute LPS of I comma j. Okay, and we're going to let T of n equal to S of I comma j, where n is the number of characters. So it's equal to j minus I plus 1. Okay. So what is S of ij? Let's do it this way. Okay, so what is T of n equal to? T of n equals, let's go back to the work that's being done. So I need to compute the two subproblems. Okay, so what are the two subproblems? I have one subproblem that's half the size. I'm sorry, not half the size, one less. So it's like a recursion, divide and conquer with a decrease and conquer. And I have another subproblem. Okay, does everyone see that? Right, so one problem. So what is T of n minus 1? T of n minus 1 is equal to the time for going from I plus 1 to j, but it's also equal to, lost a 1 there, it's also equal to the time for going from I to j minus 1, right? These take the same time, even though they're slightly different strings. And then I have to take the max of those, and that's equal to that. So who can tell me what the solution to that recurrence is? We just saw it in Fibonacci, or we saw it in the context of Fibonacci. It wasn't the actual answer for Fibonacci. Okay, that's going to be exponential time. Okay, because each time, here's another way to write it. Let's do this. Now it'll be easier to see why that's exponential, right? So each time I'm doubling, I'm reducing the problem by 1, but I'm doubling the cost. So I keep on doing that. I'm going to get a 2 to the n. Okay, so that's exponential. That's bad. Okay, so here's our dynamic programming approach. Okay, same idea, but we're basically flipping it around. We're saying, let's start with the smaller cases first and work our way up. So we build a table. Okay, here's our table. It's basically going to store the longest palindromic subsequence from point A to point J, but starting with the smallest cases. So can someone tell me, I know that it's a little bit small, but can someone tell me, you know what, I can go to full size here. Can someone tell me why this is true? Doesn't let me do that. Okay. This 4i in range n, li, I equals 1. Why is that true? I don't see the chat, so just talk out. Why is that?
It was 1 character long, so it's at least 1.
It's 1. Good. Okay, then we gradually increase the length of the string. And we say as follows, okay, if the two endpoints are the same and the length of the string is 2, so we know that that's just going to be 2. Okay, if they are the same but the length is greater than 2, then we get a 2 plus whatever we could do without using those 2 characters. So again, if the string is more than length 2 and the 2 endpoints are the same, we get to use those characters and we see what could we do so far with the middle. But in this case, because it's bottom up, we've already done the middle because it's a smaller substring. We are working in increasing order of length of the substring, right? So that's what this SL stands for. It's a length of the substring length. Or if they are not the same, then I see what can I do if I can't use both endpoints. either I omit the character on the right or I omit the character on the left, right? So I+1 means omit the character on the left. This means omit the character on the right. And now I have, I will build this up, and then I just return the longest substring from position 0 to n-1. And what is the time complexity of this algorithm? So let's look at it. Okay, so I have this code here that does initialization of that matrix, if you like, two-dimensional table. And even though it's written in one line of code, what is its time complexity? It's actually more than that.
N squared.
It is n squared. Okay. Now, can Python do that in some faster way? Maybe, but it looks like n squared. All right. Then we have a loop here for I in range n. How long does that take?
N.
N. And then I have a nested for loop. Okay, inside the for loop is simple operations, right? How long is that nested for loop going to take?
N squared.
N squared. Very good. All right. So we went from something that took 2 to the n to n squared. And maybe let's do an analysis slide here. So let me copy that slide. Did it get duplicated already? Did I lose it? Okay. I'm going to delete, duplicate that slide. And okay, so let's just make sure I still have the other one before I start changing it. So there's my recursive approach analysis. Okay, I have my dynamic programming approach. So we have, let's say, our initialization of L, okay, is O of n squared. We have one for loop is O of n, and then nested for loop is O of n squared. Total time is O of n squared. And what do we call that? You don't call that exponential. What do we call that? Two different names we could call that.
Polynomial square.
That's right. So we call it polynomial slash quadratic. Okay. All right. Good. So there will be, there's going to be an assignment to use this dynamic program approach to find this problem. Okay, so here is an example. Okay, pick the word modem. Anyone know what the word modem stands for? It's actually a contraction. It stands for modulator, demodulator, modulation, demodulation, right? Okay, so what a modem does is it basically transforms one kind of signal into another kind of signal for communication over a line, right? So you're taking, it's interesting. So when I was your age, or actually when I was younger, when I was in high school, and I remember my friend, I didn't have a computer, but my friend had a computer. His father was a professor at the University of Toronto. He's an engineering professor. And so they had a computer and a modem. Ooh, pretty cool. You stuck the phone into some kind of special slot and it picked up the signal. So what did it do? It transferred the computer signal into a phone signal. Okay, it's ironic that what do we do today? We have voice over IP. We take the voice signal and we convert it into a digital signal. So times have changed. Okay, so what are we doing here, right? So we build up the table. So first of all, you'll notice that the bottom triangle here is all 0. Why is it all 0? because you can't have a subsequence from position 2 to position 1. You can't have a subsequence from position 4 to position 3, right? So anything where the row number is less than the column number, or the start is bigger than the end, is going to be 0, right? Why is the diagonal 1? Because those are strings of 1 character each. So those obviously are going to be 1, right? Then we go from 1 to 2, and 2 to 3, and 3 to 4. So those are all 1, all right? Why is this one different, right? Highlighted in yellow, because at this point, when I go from 1 to 5, I have an M here and M there. Those are the same. So I get those 2 characters, and then I can choose any one of these 3 other characters to get that 3rd one. Okay, so here's an example of LPS using the dynamic programming approach. Oh, we do have, here's our, this is my slide from before. Okay. All right. Fine. Okay, so now we look at a different problem. Okay, this is not LPS, it's LCS, longest common subsequence. What does a common subsequence mean? It means we take 2 words and we look at what do they have in common in order, right? So if you look at these 2 words here, you can see they have some things in common, right? There's an H, and they have to be in order, and an O, and then a S, or if you prefer, an HO and an E, HOE. Both of them have HOE. Again, not necessarily contiguous, not necessarily one right after the other. All right. So that's called the longest common subsequence. Here's an interesting story. So back when we were still on campus, I'm going to say this was spring 2020. Might have even been before that, but I think it was, might have even been 2019. And we talked about this in class. I'm sorry, we talked about it in class, and then we had an exam that had dynamic programming on it. The next day, one of my students had an interview out of state at a technology company, and they asked them this very question. Okay, not this example with the house and the shoes, but they asked them this question on an interview. So dynamic programming is a common interview question, because they want to see, can you think beyond the sort of natural brute force recursive way of doing things. Right, so in the longest common subsequence, we say I got 2 strings, one of string length M and one of length N, right? How many characters do they have in common in order? All right, so if the last 2 characters are the same, so we get 1 for that, right? And we say, okay, now what happens with the rest of the string? So I have n minus 1 characters left in the first string, n minus 1 characters left in the second string, and I perform the LCS on that. Okay, if the 2 characters are not the same, then they don't automatically contribute to it. So I say, well, I look at what happens if I omit 1 character, or what happens if I omit the other character. What do I get there, right? So once again, this is going to be exponential time. The question is, can we do a dynamic programming approach? And as before, you build up. Okay, so here's what we do. So first of all, M and N are just defined as the lengths of the string, right? We create an array for keeping track of this, and then we have a loop. So it is a nested loop. And we say as follows. So if either I or J is 0, which means the length of the 2 substrings, so obviously they can't have anything in common because one of the substrings has no letters in it. So Lij is going to be 0, right? If the 2 n characters are the same, right? If the 2 n characters are the same, then we get 1 character in common, that last character, and we get whatever we can do with only I minus 1 on one and j minus 1 on the other. Yeah. If they are not the same, then I take the max of omitting 1 character on one side or omitting the other character on the other side. And that's going to be that. And what's the time complexity of this algorithm? By the way, I think, yeah. Okay, so this thing over here, again, it looks like it's one statement, but it's actually creating a n plus 1 by n plus 1 array. So that is really order of n squared. And then I have a nested loop. Nested loop is also order of n squared. So it's an order of n squared, which is much better than exponential time. And here I have an illustration, right? So again, here's one string, and here's the other string, shoes. Okay, so let's look at where it changes. Okay, so let's go from here to here. You see how it changes? So what this is saying is, so far I only had H. So H has nothing in common with S. It has one character in common with SH and one character in common with SHO. But if I introduce an O, so now I have HO over here, and I have HO in the SHO, so that's where this 2 comes from. All right, let's look at where else it changes. It changes over here because I've added an S, so that S together with that S gives me another character. All right, so this is an example of the longest common subsequence. Okay, any questions so far? Okay, so let's go back to something called matrix multiplication. All right, remember how matrix multiplication works. If I have 2 arrays, one is an m by n array, the other is an n by p array, and I multiply them by each other. So the total number of multiplications is m times n times p, and that's using the traditional algorithm. In the assignment that you just did, you saw that you could do Straussen's algorithm, and it takes n to the log base 2 of 8 of 7, which is the same. That's what this is. That comes out to be approximately n to the 2.8 or 2.81, something like that. So a slight improvement. And for large enough n, that slight improvement is a significant improvement. But that's not what this is about. Okay, that's not what we're really discussing today. We're discussing something else, which is when I multiply 3 matrices, I can either multiply the middle and the last first and then multiply that by A, or I can multiply the first and the middle and then multiply C. Okay, so either way works the same, or comes up with the same answer. We call that the associative property of matrix multiplication, right? What is not true is the cost of doing those the same. So this is sort of surprising. If you haven't seen this before, you might find it surprising. And here's what we do. Okay, so if I multiply the A and the B first, I need 10 by 5 by 1. 10 by 5 by 1 multiplications. And now I have a 10 by 1 matrix. So I take the 10 and the 1 and the 100, and that's where this comes from. And I add that up. So I get 50 plus 1,000 is 1,050. Okay, what happens if I do it the other way? I do the B and C first and then the A. So I say, okay, I have a 5 by 1, multiply that by 100. So that's 500 operations for that. Then I need to multiply by the A. So I have a 10 by 5 by 100, and that's 5,000. So if I do it this way, I need a little over 1,000 multiplications. If I do it this way, 5,500 multiplications. So just the way I parenthesize the problem, right? Which order I chose to do it in makes a difference by a factor of 5. That was just with 3 matrices. Imagine if I have a whole bunch of matrices and I could, order it one way or order it a different way, or group it or parenthesize. That's the word we use. Imagine the difference that it could have. So what we're going to do is we're going to try to model this. So first we come up with a function. It's usually a 3-step process. First we come up with a recursive definition. Then we come up with a recursive program. And then we see if we can turn the recursive programming into a dynamic program. Okay, so we say as follows, right? We're going to define Mij as the number of multiplications needed to multiply a chain beginning with matrix I, and going to matrix J. And we say if J is less than I, the answer is 0. Why is that true? So there is no such chain, right? I can't go a chain that starts in. Okay, right? There are no matrices, right? I can't go from chain from, matrix 5 to matrix 3. So there's nothing to multiply. What about the next case? When J and I are the same. So now there is such a chain, right? It's possible to have a chain with one matrix in it. So why does it still say nothing to multiply? Because I have one matrix. So I do have numbers, I have a matrix, but it's one matrix. When I have one matrix, it's nothing to multiply. All right, what about when J is one more? So now I just have a single pair, right? So how many multiplications? I need the number of rows in one matrix times the number of columns in the other matrix, which happens to be the same as the number of rows in the next matrix, and multiply that by the number of, that's a mistake there. It's the number of rows times the number of columns times, that should be the number of columns in the next one. So let me fix that. Be the number of columns, which is the same as the number of rows in the next one, times the number of columns. And in the general case, what I need to do is I need to look at, this should remind you a little bit of quicksort, right? I need to find the optimal position in which to divide it up. So if I write that recursively, here's what I get. Okay, I say, okay, if J is less than or equal to I, that means either I have in the legal chain, right? I'm going from matrix 5 to matrix 2. There's no such thing. Or it's a chain of 1. So a chain of 1 matrix is nothing to do, right? So that's this case here. Otherwise, I am minimizing, right, the best I have so far, whatever that is, the cost of the matrix chain from I to K, the cost of the chain from K plus 1 to J, the rest of the chain, and the cost of the number of rows in this matrix, the number of rows in the other one, and this is the number of rows in the matrix after the chain, which is the same as the number of columns at the end of the chain. Okay, if I do it dynamic programming, so I'm doing bottom up, right? So this says, okay, anything that is going from I to I, there's nothing in there. I don't even bother with the lower triangular, right? So this is the diagonal, but we could make everything 0, right? So we really, initialize the MII to be 0. And then this is doing the minimization. So say, taking the same code, the difference is, it's almost like the difference between parentheses and brackets, okay? What's the difference when students, this is true of Java and Python, so I don't know why students get confused, but what's the difference in code between parentheses and brackets?
I think parentheses tell the order to do the operations, right? Brackets is.
So I don't mean parentheses, if you're ordering something. I'm saying if I say like M parentheses versus M bracket.
Parentheses is a function call, bracket is.
Okay, that's what I want to hear. So parentheses is a function call and bracket is like a list or an array, right? So here I'm doing in a recursive implementation, it's a function call, right? I could have called this M, by the way. I could have called the name of my function M, and then it would have been basically look almost like the next slide, except the difference here is I am using my array. I'm using a 2-dimensional array of my 2-dimensional list, which stores the previous results It's storing the previous results, so I don't need to compute it again. All right, so let's do our analysis. Okay, if I use a recursive approach, it's O of n 3 to the n. Why is this one 3 to the n and the other ones were like 2 to the n? So look at the code here. In this case, I'm not just taking the left and the right and finding the min or finding the max. I am iterating over those possibilities. So this, I should look at the recursive one, right? To find the min, as k goes from I to j. So on top of all the recursion, I also have a loop. And the loop from a recursive context comes out to make it another factor. So it comes out to be 3 to the n. Okay, whereas a triple nested loop, which is what I see here, right? Nested, nested, nested. That's where the n cubed comes from. Okay, so I have a matrix, a helper matrix, which takes up n squared space. All right. In theory, I don't have any auxiliary storage, but in reality, there is storage related to the stack. So don't think that it's not going to take some. By the way, in my 220 class, we did the same search algorithms assignment. We just did it together in class yesterday. And in addition to the ones we did with you, we did a non-recursive binary search. And the non-recursive binary search was so much faster than the recursive binary search, okay, which is very interesting, right? So the recursion just adds a lot to the cost. Okay, there is a third approach. Okay, the third approach is a hybrid approach. It's called memoization. Okay, memoization says we're going to use a recursion because we like recursion, but we're going to store anything that we've done before. Okay, so we say when I call MCM I of k, it's going to call this, and I say if I have the number already, right? So let's say I use -1 to initialize array. If I have the number already, it's greater than or equal to 0, then just return it. Okay, so the advantage to this is we retain the recursive structure, which is sort of makes sense. Also, in a bottom up, you need to compute everything, even the things that you don't necessarily need. But because it's bottom up, you need to fill in all the holes as you go, right? In this memoization approach, you only need the prior results that you actually need. So you don't have to compute everything necessarily. That said, as I just pointed out before with the binary search, recursion is expensive. Okay, it's deceptively expensive because we don't think about the cost of recursion itself when we write recursive code. We encourage, as computer science teachers, we encourage you to think recursively and to program recursively, and we don't take into account the cost, the overhead of recursion. So in fact, the dynamic programming would probably be better in this case than the hybrid approach of the memoization. All right, how are we doing on time? All right, let's finish the slides. Okay, so this is more in terms of a sneak preview. Okay, so our next major unit in this course is graph algorithms. We'll spend 3 or 4 lectures on graph algorithms. And then even after that, some of the other topics will relate back to graph algorithms. So one of the most famous problems in graph algorithms is called the all pair shortest path problem, APSP. And it says as follows: if I have a bunch of points, right, what is the fastest way to go between each pair of points? So for every pair of vertices, every pair of nodes, what is the fastest way to go? So on the surface, that sounds like it's going to be very expensive, right? Because there are a lot of possibilities. Even if I'm not allowed to repeat any vertices, so if I have, n minus 1 possible intermediate vertices between 2 points, or n minus 2, right? Because if I don't repeat the endpoints, so if n minus 2 factorial, or maybe it's not factorial, I can choose which ones. So we're talking about something in the exponential to factorial range. Okay, so that's very expensive. It turns out, though, we can use dynamic programming to solve this problem. Okay, so I want to show you, it's called Floyd's algorithm. And here's the code. Okay, so we'll come back to this when we do graph algorithms, but I want you to see something here. So first of all, we initialize it. Okay, so most dynamic programming, you're going to have to initialize something up front. So we say that the distance, the shortest way to go from I to j is just the current edge from I to j. In other words, not an elaborate path. You just take the straight edge, whatever that is. And we have pred. Pred is on the path from I to j. What is the immediate predecessor? Well, if the path is of length 1 so far, then the immediate predecessor of j will be I, right? And then we get to our loop. Okay, so first of all, how many nested loops do we have here? Three, right? So I have a for k, for I, and for j. Here's what I want you to remember, right? The intermediate vertex, right? So we're going from I to j with an intermediate vertex k. The intermediate vertex is on the outside of this loop. It's the most outermost loop. Okay, so what are we saying here? We're saying I have some path so far that takes me from I to j. Can I do better by going through intermediate point k and then from k to j, right? So if I go through point k, does that make it better? If it does, then let's make that the new best way to go from I to j. So we say, okay, I'll go from I to k, and from k to j. That is better than what I had before. And now the predecessor on the path from I to j is whatever the predecessor is of j on the path from k to j. So I have a table here. This is taken from Wikipedia, and it shows you as k increases, right? As my intermediate increases, I gradually fill this in. Everyone see that? So initially, anyone know what infinity means in this context? Why do I have an infinity sign there?
There's no way to get there from.
Well, it means there's no edge. Okay. So initially, this reflects when k equals 0, that means I have no intermediate matrix vertices. So it means just if I take a plain edge, not an elaborate path, a plain edge, then I say, well, what happens if I can introduce one intermediate vertex number 1? Okay, does that change anything? Then this says, what happens if I can introduce vertex, an intermediate vertex number 2? Does that change anything? Then I say, and I use the previous results to help me. Then I say, if I introduce intermediate vertex 3, what happens if I introduce intermediate vertex 4? And slowly but surely, I'm able to get rid of things. All right, so get rid of some of those infinities and get shorter paths there. Okay, so if I look at this code, what's the time complexity? So I have 2 loops. I have an initialization and I have a main loop. The initialization is a nested loop, double loop. So that's v squared, v is the number of vertices. And the main loop here is 3 loops, so it's going to be v cubed. Okay, so instead of some kind of exponential time, which is what you might expect, all right, you get it down to v squared for initialization, v squared for the main, and a total time of v cubed. All right, then we have something called the Warshaw's algorithm. Warshaw's algorithm is sort of like the algorithm we just saw. The difference is here we don't care about cost, we just care about whether there is an edge or not. So we're saying, we call this a transitive closure. It's basically like connectivity. Is there a path? So he's saying there is a path from I to j if there is currently an edge from I to j. Then we have our nested loop, and we say as follows. If there isn't a path yet, but I can go from I to k, so it's true or 1, and I can go from k to j, it's true or 1, then there is a path from I to j, and we set the path from I to j equals 1, meaning true or false, right? There is a path. So Warshaw's algorithm is very similar structurally to Floyd's algorithm, so much so that in some books, they don't even call them separate algorithms. They just call it the Floyd-Warshall algorithm. They're so similar. Okay, and again, the analysis is the same. And we have the knapsack problem. So remember yesterday, we did these problems and I said, we're going to do them again in this context. So the fractional knapsack problem was a knapsack problem where I can take part of items. And we said a greedy strategy works. Then we talked about the 0-1 knapsack problem, where I can either take an item or leave it, take it or leave it. And we said that requires exponential time, or at least that's the only way we know how to do it optimally. But we said that with 0-1 with an integer weight capacity, meaning the knapsack can't just contain any number, it can contain only integer weights. So 0, 1, 2, 3, or so on. And here it is. Okay, so take a look at the code here, right? So in this line here, we initialize it. Okay, it's a one-dimensional array. I'm sorry, it's a two-dimensional array. And what are the 2 dimensions of the array? One dimension says which items we're including, and the other one says the capacity, the weight of the knapsack, you know, how much it can hold. So we start it from 0, or we work our way up to W, which is the maximum capacity. And let's look at the guts of the code. So this is saying as follows, right? If I can't have any items, or the capacity of the knapsack is 0, so W is like the weight, it's, you know, how much weight it could have, then obviously the best I can do is 0 because I have no items or I have no place to put them. If the weight of a particular item is less than the remaining weight, then I see, okay, how can I do better? If I include the item, so I include the value of the item with whatever I could do without that weight, and I compare that with what I can do without the item at all, but retaining that capacity. So I have 2 choices. I can either use some of my capacity on this item, or I can say, you know what can I do without it? Can I do better, right? And then the third option is if I can't take this item because it's not going to fit, then all I have is what could I do without the item with the same weight? So this is the dynamic programming version. And what's the time complexity of this? So I'll give you, we have 2 nested loops. We have one nested loop for this list comprehension for the initialization. And then we have another nested loop, basically the same size, more like a traditional nested loop. So it's the number of items times the integer capacity. So we can do dynamic programming in roughly n squared, right? So just to wrap that up, okay. So what is dynamic programming? Dynamic programming is a bottom-up approach, right? So typically we like top-down, right? Merge sort. What did merge sort do? It took our big array, broke it up into 2 parts, solved the left, solved the right, put it together. Quick sort broke it up into unequal parts, solves the left, solves the right, puts it together. So that's how we're taught to think, especially when we learn about divide and conquer. This says do it the other way around. Start with the small cases, which are easy, and gradually work your way up using an incremental approach, right? Figure out the case n+1 based on what you know about the case of n. It's almost like an inductive kind of proof, right? For it to work well, it needs what's called optimal substructure, right? So think about like the matrix chain, right? The matrix chain works best knowing how well I can do the left or how well I can do the right. That helps me find a better solution to the bigger problem. And then we also talked about the hybrid approach, memoization, which retains a recursive structure, but it keeps track of any work, any computations we've done, so that we can just refer back to those results. Okay, and these are the examples that we did today. Okay, so we had the one-dimensional closest triple. All right, it's still O of n. Let me just write that in there. So it was, I'm sorry, it was O of, so it's still O of n cubed, but reduced time by a scalar factor 3/4. So that's not so impressive. Fibonacci sequence We had major improvement. Kidane, major improvement. Longest palindromic subsequence, major improvement, right? So a lot of major improvements going on here. And I think that's it on that. Okay, so what I'd like to do now is I'm going to stop the share. And I haven't formally finished the assignment, but I'd like to get you started on assignment 5. So we have, how long do we have? We have 25 minutes. So do we have a volunteer who would like to get us started on assignment number 5? Should I do eeny, meeny, miny, mo? Yeah, volunteer. Ming, you want to go?
I don't have PyCharm on
You
this
don't have
computer,
PyCharm.
but
Okay, all right.
I have support.
Who,
3.
someone else? Omar? Okay, let's go through the list. What I see left on the screen. Sagar,
Sure. I mean, I'm opening. I could do it actually.
okay. I need to enable the screen sharing. Did I enable it? Are we on your screen or mine?
I think it's still yours.
Hold on.
Is it good now?
You should be good to go.
Okay. This is the assignment file, right?
Yeah, the assignment itself is not complete. I mean, it's got some links in there which are useful.
Assignment. Oh, so it's not gonna take anything from the previous assignments, right?
It works differently than,
Okay, so
Yeah. so. Okay, either way, just if you can open your PyCharm, show us your PyCharm.
oh, you can't see it?
Nope.
Oh,
Okay, so let's change the name to assignment 5. Do you have access to your code here or no? Your old code?
The previous code?
Yeah, it's just sometimes helpful to grab stuff, but otherwise we'll just type it again. Yeah, yeah.
Oh yeah, I could actually.
So I generally recommend that students take their previous assignment and copy it. So, you know, just saves time.
Okay, let me see if I could.
I mean, we could type it ourselves. Just change the name. It's okay. We'll manage.
I have the previous one. You want
Okay,
me to-
so grab one of them, please.
So the.
Okay, so go to the top. So you're going to call this one assignment 5. And you can put a dash there. You could say palindromic subsequence.
Oh, this is it.
Yeah, you could write exactly. Okay. You can leave those import statements there for now. Go to the bottom. And okay, you've got that there. Okay, good. So for now, let's just, we're going to code the example that's in the slides.
Oh, my bad.
Example that's in the slides, and it's also in the assignment. So in the beginning of the main, you could say S equals for string. And then we're going to get a little more interesting with the strings. But for now, just do S equals. So at the beginning of your main, please. Say S equals. And copy in that string, the Queens College of CUNY.
Oh,
Okay, good. Now let's copy the code for the longest palindromic subsequence. So I have 4 links there, all right?
mhm.
One is the palindromic, and one is the substring, and one is the.
So
So we do
this
not want, that's the brute force. We do not want the brute force. Okay, yeah, you could grab that.
From here.
I guess so.
Okay.
We don't need the, yeah, that.
We do. Okay.
Here's another technique. You see that thing on the left? It allows you to select everything, and then you can delete the parts you don't need.
Oh, this.
Go up a little bit more. That's copy.
Okay.
So create a new function there. You could call it, I'm calling it a new function. Okay, and we're going to call it LPSS. You could do it in lowercase, LPSST for substring. Okay, and we're going to pass in a string. Well, S, you could say S, and then a colon. Okay, and paste in the code. Okay, so now get rid of the garbage from it. Okay, so basically you can get rid of that import. Yeah, all the way up. No, what are you doing? Just delete the garbage. So from there, from line 29 up. Yeah. No, you keep your definition that you made there.
Oh, my bad.
Okay, we're using our name. So get rid of their name. We have our own name. Okay, and you got to fix the indentation. You can also change their STs to S's. Okay, so get rid of the blank line, get rid of 15. Again, I'm not a big fan of their comments, but you can keep them if you want. I like,
No, I'll remove them. Change signature, that doesn't allow.
just, it's okay. You're gonna go through it in O of N algorithm to go through the code anyway, so just change it as you go. This will force you to look at each
Oh.
line. It's okay, just change it. Okay, next line, get rid of. I would just make a linear pass through the code and get rid of any garbage.
And also I'll just remove all the.
No, undo.
Oh, okay.
Just
Oh
do a-
yeah.
Okay, do a linear pass. Start at the beginning and go through it.
Mhm.
Okay, get rid of the garbage as you go. Fix it as you go. So you'll make one pass through, O of N time. Okay, those two lines can be combined into one. That table, no, before you go on, linear pass through. One, there you go. Get rid of the blanks. Just do it in order. Just clean it in order. Okay, clean it in order. Line 19. Okay, look at anything that's underlined you want to fix. Okay, so max length, put an underscore in. Just let PyCharm help you. Lowercase l. Okay, get rid of the parentheses in line 19, redundant parentheses. Get rid of the blank. Line 22. Line 28.
Yeah.
Get rid of the comment, get rid of the blank. Now go up, keep it in order.
Oh yeah.
It combined those two lines, 35 and 36. Okay, get rid of the redundant parentheses. Good. Just be careful if we didn't lose indentation there. So we can get rid of 37.
And this one I think.
Okay, so we can you can move that onto one line, the print and the. Okay, what we're actually going to do is we're going to return the substring. Okay, so the substring. So create a new variable in line 42. Actually, you don't even need a variable. You're just going to return max length, comma. You don't even need the max length. You could just return the string. Okay, the substring is going to be S bracket start colon start plus max length minus 1. So exactly what you see in the previous line.
Okay.
No, it doesn't say start length. Start plus max length plus 1 minus 1.
Oh,
That's what. Okay, and now you can get rid of line 42. And you can get rid of line 45. Okay, so let's get rid of random matrix. Get rid of that garbage. Get rid of the random matrix. Good. Get rid of the print matrix. Okay, get rid of native molt. Get rid of simple molt. Get rid of Strawson. Okay, hold on to the plot time in case we go back to that. Okay, in your main, comment out everything you have in the main except for that string. Okay, comment out the data frame on the bottom. Okay, and now call that thing.
Here.
Yeah. You could just say print SS, whatever. Call your function. Okay, better yet, create a variable. Okay, so we'll call it SS equals. Call your function. Okay, and then you print SS and len of SS. No, you need to pass the S in. Print, let's do all three, S, SS, and len of SS. Or even better, S, len of S.
No, len.
It's a function, len S. Yeah, and then SS. And then len of SS. Okay, and let's see what we get.
Oh, I think it's
All right, you can comment out the pandas on the top, but you don't need to install it now.
The panda one, not the other one.
You don't need any of those right now. We'll introduce them back as you need.
He needs a plot, right? Oh no. I don't.
Well, pot is being quoted, so yeah, you need to, I guess. Yeah,
so I think I need to install this.
I guess so. Yeah, see, that's the advantage. You don't really need to create a new project, just change the name of the assignment. But okay, it is what it is. Why don't you call this assignment 5? So while we're waiting, can you change the name? Right click on the main. No.
Refactor. Nothing.
It's running, so you can't.
We don't. I'll just comment out pandas.
Okay, I think we are just losing one character at the end. So go to the bottom. So we found the right position. Go to your LPST and return instead of max length -1, let's do max length. Okay, run it again. Okay, Good, so we have a few minutes left. Let's see if we can do the other one. Okay, and then so go to the bottom. You need to print the, no, it's not the substring. It's not the substring, it's the subsequence.
So should I go here and
No,
get it?
go back to the assignment. We already did this one.
Mhm.
Go back to the assignment, go back to the description.
Oh,
Go to the last one, print longest palindromic subsequence.
so from
Print longest palindromic subsequence. No, look at the links. Look at the links. Print longest, fourth one.
oh the fourth. Oh, okay, my bad. The first one.
Is this, I think this is, does this print it? No, that is
I-
gonna give you the Okay, so, yeah, you could grab that code, that's fine.
Okay. Should I call it?
Well, I called it LPSSQ.
And pass in it.
It needs a string.
So I'll just name it as this. That's fine, right?
Yeah. Okay, so it actually requires another function, okay? So you can pull out that whole function there, just pull it out. Pull out the LCS, pull it out,
Remove-
extract it, make it a separate function. Pull out that code.
Oh,
No, don't do it like that. Just extract it because you want to retain what you have at the end.
You pasted two functions, so that this is the first one. You got
Correct.
this. It replaces. Copy it from 47 and go down.
Undo.
No, copy it from 45, the line.
all the way
No.
to down.
No,
Yeah.
you need the 45 also.
Yeah, he has to copy the whole thing. Go down. Slow.
No.
Slow. Go up. Go
No,
up. Slow.
Up to the return ANS.
The 79 to
Up to
79.
the return ANS.
Okay.
Cut this Control X. Oh,
Now where did
now,
Where do you
now
want-
Anywhere outside this function, just not inside this function. Not
Outside.
inside the function.
okay.
in 43, line 43. You paste it the same place again.
Before, okay.
Scroll down to the, and remove the 87. Remove the line 87.
Yeah, get rid of from 87 up there. Stop, delete. Okay, now clean that up. No, I didn't say delete. Clean it up. Get rid of the garbage.
Oh, okay.
Okay, what's that LCS underscore? Where did that come from? Is that the name of a function?
It was the previous function. Yes.
Yeah.
It had an
The-
underscore in it, the LCS?
I. Yeah.
And what is that referring to? Is there a function called LCS underscore?
Yes, the big one.
The big one is LCS?
Yeah.
Okay.
Yeah.
Why don't we just call that LCS? I don't understand what's underscore. So just change the name. Okay. And
Mhm.
hold on, the signatures don't oh. Okay, good. So fix up the indentation in that. Yeah, you're over indented though. Now go higher up. Fix the indentations. Start from the top. Should be units of 4. Python is units of 4. Is yours set up for 3? Go to another function that you have. Are you in units of 3 or 4? Python should always
Yeah.
be units of 4, okay?
Yes.
Like in plot time. So let's be consistent. So go to line 46. Okay, I would use your tab, but. Oh, you know what your problem is? The problem is line 44.
Oh.
That's not your
Oh,
problem.
yeah.
Tab. Use your tab.
Okay, so I think this is okay.
Yeah, get rid of the blank line. Get rid of the parentheses. Previous line. No, not that. No. The LII. You go linear. Go straight. Fix your lines as you go. So line 51 needs to be is over indented. Okay, now do the LF. Next line, unindent. Now go linear. 52, fix 52. Now, good.
This also.
Yes. Put them on the same line.
Oops.
Okay, so LCS is being that, okay. LCS here looks like it's some kind of array. So let's change the name in line 57. Let's call it LCS2. Just change it. I don't know exactly what that is, but and then you got to change it in line 61. Get rid of the parentheses in 65. Okay. You can try to run it, otherwise we're gonna stop, but what are the errors? Okay, we don't need that driver code. Get rid of line 78 through. Get rid of that. No, get rid of 70. We don't need that. 78, 79, 80. Okay, in your main code, you need to call it though. So go to your main code and say SS2 equals LP SSQ of S, and copy your print statement from line 99. And print SS2 and len of SS2. Okay, we have two errors, unresolved reference string, click on those. Okay, that's S. Should be just S. Okay, we'll click on the error. Okay, that should be LCS2, and the next line LCS2. All right, so it looks like we have a bug. Okay. So, all right, we have it set up. We just need to make it work. All right, so we're going to stop here. And, you know, you could probably print some stuff out to figure out, but it should come out. We should get a 9-character palindromic subsequence.
Oh,
Okay.
okay.
All right. Thank you, Sagar.
Thank you.
Okay. Bye-bye.
Professor, I assume the due date on the assignment 5 is wrong.
It's what?
23.
So what?
Due date.
What about the due date?
What's 23 says on assignment 5?
It says 23. No, it should be. That's carried over from the last one. It's like, I think the 26th.
6.
Professor?
Yeah.
For like certain hashes, like the quadratic hash, what should we do if we just run out of like available new index? It's like eventually it'll loop.
So you shouldn't have. Oh, you're saying if it's
Let's just say it happens to be
if it doesn't find them, right? I mean, I said make the size the number of elements, but if you want, you can make it bigger. Make the whole thing bigger. Just be consistent about the the cases.
Yeah, okay, yeah. Because when I tried with all the same number of elements, the quadratic hashes had like as long as
The problem is the quadratic hash function is probably not full cycle, so it doesn't hit every position. If
Yeah,
it hit every position, then you would eventually find it.
well, I didn't know which values of A, B, and C to choose to hit every
Yeah,
position.
I understand. Right. So yeah, you could make the hash bigger.
Okay.
Okay. Just don't make it too big because then you'll probably still have collisions, so it's okay.
With twice the size, I think it worked out fine.
Yeah, okay, that's fine.
Okay, I think.
Okay.
Oh, wait, one more thing, actually, sorry.
Yeah.
How like specific is the, I guess, parameters you have to pass into the functions that you listed? Because I know that when we did it in class, we changed the parameters of the source function to include the item, which made sense.
Sorry, repeat the question?
Like, you told us which functions we had to build, in at least assignment 4. You wrote that we had to like search with the key, and when we built it, we only used the key. But in class, we changed the parameters of those functions. We had a key and the item that we had to search for.
Okay, so, well, the key is the item. So you have the,
Oh, sorry, and the table. Sorry, we included the table.
yeah, so I mean, you have two choices. Either you make the tables global variables, or you can pass them in. The thing I am particular about is that you keep the signatures consistent so that you can run it in that, you know, consistent fashion that I described, because otherwise people end up running each thing separately and you get a lot of redundant code.
Okay, that's not.
You can pass in really whatever you want as long as they're all consistent.
Okay, yeah, that's what I was gonna ask. 'cause
Okay, so just as an example, in my 220 class, which I'm going to do in 10 minutes, I'm adding in the sorting assignment, we're adding another parameter called verbose, and I'm going to have them put a print statement inside the code inside each sort that says if it's verbose, then print out the contents of the array. So not only do we, you know, get experience with the timings, but you can actually see how the array changes over time. So, you know, we're just going to do that for all of them so that you can call it with verbose is true or verbose is false.
Okay, that makes sense.
Okay,
Okay, thanks, Professor.
okay. Don't forget about the top hat for anyone who's still here, 7341. Okay, so 7341.